Hello everyone, and welcome to the rotational inertia of point masses PostLab, our first step along the long path to being able to calculate the rotational inertia of various rotating objects. So this lab was a little long, right? We had to do it in 3 parts. Part 1 was when you figured out the rotational inertia of just the rod, so that you could subtract it off the other 2 parts, so that we could focus on just the point masses. Right? Part 2 was when you varied the mass of the point masses by adding those little slotted masses onto them, and then measured the resulting experimental rotational inertia, in kilogram meters squared, right? And the mass was in kilograms. When you graphed that, you hopefully got a nice linear graph going through 0, 0, which tells us what's the relationship? Yeah, they are proportional. So we've said all along that rotational inertia kind of functions like the mass does in F equals ma, right? And in fact, it is proportional to that mass. Right? So if you double a rotating object's mass, it will have twice the rotational inertia. It will be twice as hard to change its motion, its rotation. Okay? 3 times the mass, 3 times the rotational inertia. Of course, it's not the only thing that's going on, but it is one of them. Right? So if we make a little math model out of our linearized graph, the y variable is, of course, the rotational inertia, and that equals your slope. Now, I'm just going to throw in a theoretical slope here. I will explain why I chose this, okay, in a little bit, and we'll compare it to what you got actually in the lab. You can feel free to put yours in here. If you've submitted it to the Google form, then you have something that is in the ballpark of 0.0324. Give or take a few, whatever this is out here, tenths, hundredths, thousandths, 10,000ths, probably. Units, it's a slope, so rise over run. Units of rise are kilogram meters squared. Units of run are kilograms. And of course, if you check out those units, the kilograms will cancel, leaving us with units of meters squared. Interesting if you think about what else we did in this lab, but we'll get there. X variable is, of course, the mass, and the y-intercept is 0 because if you have no mass, you don't have an object, so can't have any rotational inertia. Don't forget that in this part of the lab, right, you kept those masses a constant distance away from the axis of rotation. Should have been about 18 centimeters, 0.18 meters. If you measured from the axis of rotation to the center of mass, right, of those point masses on the end of the rod. Now, the third part of the lab was where you varied the distance to the masses and kept the total mass constant. You just used the point masses and their screws, and then measured the resulting rotational inertia. This one was a little tougher. When you graphed it, you should have gotten something like that. That, of course, is a top-opening parabola, and we've seen this pop up many times in nature, and we know that to linearize this, what must you do to your x variable? You must square it. Right? So if you graphed rotational inertia in kilograms meters squared versus distance squared in meters squared, right, that gave you a linear graph that went through 0, 0. Right? Which means, what's the relationship here? Well, we look at our linearized graph, right? And since it's linear and goes through 0, 0, we can say that the rotational inertia is proportional to the distance squared. This, again, is the distance from the axis of rotation to the center of mass of our point masses, to the position of the point masses, essentially. So notice that means if we move our masses, our point masses, twice as far away, you don't end up with twice the rotational inertia, you end up with 2 squared, or 4 times the rotational inertia. If you triple their distance, 3 squared, 9 times the rotational inertia. So notice here that changes in distance actually play a bigger part than equivalent changes in mass. If you double the mass, you get twice the rotational inertia, but if you double the distance, you get 4 times the rotational inertia. Right? So that's an interesting thing to pick up about rotational inertias and mass and orientation of that mass. So let's make a math model out of course, our linearized graph. Right? The y variable is I. Again, I'm going to give you a theoretical rotational inertia, and I'll explain why that is, why I chose that number in a little bit, of about 0.171, which should again be a few thousandths away from what you got, right, if you put this into the Google form. Units, rise over run for a slope. Units of rise, kilogram meters squared. Units of run, meters squared. And notice what happens. The meters squared cancel, and we're left with units of kilograms. Kilograms, units of mass. The x variable is r squared, right? Not distance. That is not linear, right? It's r squared. And the y-intercept is 0. If the mass is at the axis of rotation or on the axis of rotation, I guess it can't really spin. Right? No distance away. So this then is our math model for this part 3. And in this part of the lab where you varied the distance, you kept the mass constant. And if you brought your 2 brass masses and your 2 screws over and massed them, it's probably pretty close to 171 grams, 0.171 kilograms. No, we'll get there. Just hang on, folks. So, where do those slopes come from, right? And how can we put these 2 equations, these 2 parts of the lab together into one math model? We're going to do this a little bit differently in this one because of just kind of how everything's set up and how it works. So this was the first, or part 2 of the lab, I guess. In this case, you varied the mass, and this is one of those weird cases where you've got m's functioning as 2 things here, notice. An m as a unit is meters, an m as a variable is mass. It's all about context, people, right? So our constant distance was 0.18 meters. That's from the axis of rotation to the center of the point masses, center of mass of the point masses. So what does this slope actually mean? Well, let's take a look at our lab results. And I've got more than just your year in here. I've got several years because I wanted to be able to see it, and there's usually not a lot of groups in APC. So you can see I go back all the way back to 2018. And let's look at these 2 columns to start out with. Don't worry about these 2 on the right. We'll get there. This is the distance from the axis of rotation to the masses, which you notice is supposed to be 0.18. And yeah, that person got 0.185, and I'm going to change that because it's not 0.185. It's actually 0.18. It has to be. That's the way the equipment's set up. And then these are everybody's slopes. And you'll notice, like I said before, they're all pretty close to one another. Right? If you look at these, they're not very far apart. And as an average, it's about 0.0329. Now, how might these be related? Well, if we go back here and we look, right, this is where we had the units on your slope were meters squared. Oh. So maybe let's try squaring the distance. Right? 0.18 squared is 0.0324. Oh, look at that. It is essentially the slope that we got on our linearized graph. And as a class, we're off by about 1.5%, okay? Now, if you look at the percent errors, and I just basically calculated the percent error between 0.18 squared and what you actually got as a slope, so again, yours are these last ones down here, right? You can see that these are probably a little bit bigger than some of the errors we're used to in our labs, okay? I think that we get a little bit more error in this lab for a couple of reasons. The biggest one being that the equipment wasn't intended to do what we did with it. It was something I came up with. I had to use a different kind of screw, just happened to have these masses that added to it. I don't really think they intended for you to put that much mass onto that bar. And so I have a feeling that it does something to the axis of rotation, right? And so we get a little more error that way. I don't think it likes having all those masses piled on there. right? So it provided some error. But the nice thing is that that's why we take lots of data and we average it out. So you can see some that are above, like here you had one that's 7.4% off, but we also had a negative 8% off. So it all kind of averages out in the end and should be fairly convincing that your slope was pretty much your distance squared. So if the slope is the distance squared, and this is the, I'm calling it now total mass, this is the total mass of your 2 point masses, right? You had one on either side. Well, I can flip the order because it's commutative, right? Multiplication. And the total mass would be the sum of your 2 masses. In this case, they're exactly the same, so I didn't have to call them M1 and M2. I really would have loved to have done this lab with a different mass on each end of the rod, but that would have provided a torque and it would have thrown the equipment off even worse. So I kind of had to use equal masses on either end. So we'll just call them M and M. If we distribute that through, we get mr squared plus mr squared. Okay, so that appears to be the rotational inertia. We take the mr squared of one mass and we add it to the mr squared of the other point mass and we get the rotational inertia. What about the second half of the lab? Here we had a theoretical slope that I said was about 0.171 kilograms times r squared. You kept the total mass at about 0.171 kilograms. Can you tell what this slope is supposed to be? Well, let's check out the data anyway. Again, this is several years worth of data. And if you look here, you can see that these slopes, right, are all pretty darn close, on average 0.173, are all pretty darn close to the total mass of your 2. I don't know how somebody got 0.167 here. A little disturbing, but oh well. But anyway, we end up with about the same thing, right? It's off by a little more than 1%. So you'll notice that it's similar in percent error, but individually the points are much closer, right? See how these errors, like the biggest one, here's a 4.8, but that's really an outlier. We get a lot of point whatevers, right, here. So this one is more accurate. And again, I think it's because we just used the point masses that came with the equipment. We weren't piling more masses on there. They intended for you to be able to slide those around, right? Probably got a little bit of error because you had to change the angle of the one pulley to make the string not hit the mass, right, when you had the small distances from the axis. But it was what we could do with the equipment, right? So it appears here that, as it looks here, that your slope of the second part of your lab, part 3, was actually just the total mass. Right? It was the 2 point masses and their screws. And of course, total mass can be written as M plus M. And if we distribute through, so it looks like in both cases, our lab is telling us that the rotational inertia of point masses is basically summing up the mr squareds. And this would be from I equals 1 to n. This again is summation notation, which we saw in a similar way for a center of mass. Different equation. It was 1 over the total mass times the sum from I equals 1 to n of all of the miRi's. No squareds. Right? And it was a vector. This one's not a vector. It's just an amount of inertia, rotational inertia. But it's the sum of all of the mr squareds. Important thing to remember. Okay? So this appears to be what we have experimentally for the rotational inertia of a system of particles. Now, the nice thing about this is because it's not a vector, like center of mass is, it doesn't matter if your object has masses all in a straight line, like in our lab, right? Or whether, what if we had 2 rods that were at right angles to one another and we had 4 masses on it, if you can imagine what that would look like? It would just be 4 mr squareds. Right, if they were all the same mass. So it doesn't matter that some are perpendicular to the other ones. It doesn't really matter where they are. It only matters how far away they are from the axis of rotation. With me there? No vector stuff to make this more complex. Well, hey, when we can, always like to do a proof of what we found experimentally. So consider a simplified thing here, which we couldn't do in the lab because it would have provided a vertical torque and messed with the equipment. What if we have a mass out here, just a single point mass, which this would be a massless frictionless rod, or massless rod, frictionless, doesn't really matter, massless rod, right, which we couldn't really do in the lab, but we can theoretically. Okay. Let's say we apply a force onto that mass. That force, of course, would provide a torque and make it rotate counterclockwise, so positive. Let's say it is a distance r away from the axis of rotation. So the distance from here to the center of mass is r. Then we know from Newton's second law that the net force is mass times the acceleration. In this case, the acceleration would be tangential because the force is tangential. That's the way I decided to draw the force to make life easy. Okay, and there's only one force, so the net force is that force. But, two things we can do here. Remember, torque is R times F. It's the size of the force times the, in this case, because it's already perpendicular, right? This is the lever arm. Which means that F is torque over R. Then we can plug that in right there for force. We also can take the tangential component of the linear velocity of the mass and turn it into the angular velocity of the whole thing, because the tangential component is equal to alpha times r. And we can plug that into here and basically turn this linear equation into a rotational equation. So it'd be torque over r equals m alpha r. These are now alphas, right? This is a's, these are alphas. Well, multiply by r, regroup, because I can, and we get the torque is equal to mr squared times alpha. And that looks a lot like kind of half our lab, right? In our lab, we actually had two masses. So this is proving that one mass a distance r away should have a rotational inertia of mr squared. Now, what if there are n point masses with a torque applied to each? Well, then the net torque would just be the sum of all the torques. Right? Torque 1 plus torque 2 plus torque 3 all the way up to torque n, right? Where n is the number of point masses. But of course, each torque would be given by mr squared times alpha. So if we plug those in, notice we have to differentiate, right? Each mass could be different, and each r could be different. So we have m1 r1 squared alpha plus m2 r2 squared alpha all the way up to mn rn squared times alpha. But you might be saying to yourself, wait a minute, how come it's not alpha 1, alpha 2, alpha 3, alpha n? Well, if this is a rigid object rotating about a fixed axis, like this, or in our lab, right, then isn't the rotational inertia, isn't the angular acceleration the same for a rigid object rotating about a fixed axis? It is, right? They have to be rotating through the same angle in the same time, right? Because it's rigid, and it's rotating about a fixed axis. So these alphas are all the same, which is why I didn't have to subscript them, and why we could pull that out of the right side, right? Factor it out. And notice what we have here then. Right, we have the net torque is equal to the sum from I equals 1 to n of all of the mi ri squareds times alpha. And if torque equals I alpha, Newton's second law, then that means I has to be exactly what we found in the lab. So this is the rotational inertia of a system of particles. And again, it only matters how far away those particles are from the axis of rotation, not kind of how they're oriented in space. Okay, so we don't have to worry about like center of mass here. Okay, it's just how far away they are, which is going to make some of the problems you're going to do on the next worksheet a little easier. So here's a proof, all right, allowing us to show here really that the rotational inertia is the same as we found in the lab. It's proportional to the mass. It's proportional to the distance squared. Important that you remember that. But this is just for point masses. What happens if things are more complex? Well, we're going to need some more complex math, and we will get to that in the next several days. But for now, point masses. So let's say here that we have two 2-kilogram point masses. We can treat them that way if we just use the center of mass. And they are separated by a thin, massless rod 4 meters long. So I'm calling it L here so I can work symbolically, but L in this case is 4 meters. So I'm going to figure out the rotational inertia about an axis through its center of mass, perpendicular to the rod. Well, where would the center of mass be for two 2-kilogram objects? Yeah, it would be right in the center, right? Symmetry. So there's the center of mass. So, rotational inertia of this system about this axis would be the sum from I equals 1 to 2, because there's 2 point masses, of all of the mi/ri squareds. If we expand that out, we get m1r1 squared plus m2r2 squared. Now notice the axis is here, so if we're calling that 0, neither of them are at 0. Okay? But each one is how far away from the axis? Well, if this whole thing is L, then each one is L over 2 away. Okay with that? And these are not vectors. This isn't center of mass, so it doesn't matter that this one's to the left L over 2 and this one's to the right L over 2. They're just L over 2 away. Not to mention it gets squared anyway, right? And because they're both 2 kilograms, I'm just going to call their mass M. All right, I want to work this out symbolically. I'll plug numbers in at the end. All right, so I'm just going to call that M and M. So, if we square each of those, right, L over 2 becomes L squared over 4. So we have 1/4 ml squared plus 1/4 ml squared for a grand total of 1/2 ml squared. If we then plug in the M and the L, and notice this is just 1 M, you just got to put it in once, right? So you get the 2 kilograms here, and that's 1 L, which is a total of 4 meters, right? And then you got to square it. 1/2 times 2 is, of course, 1. 4 squared is 16 kilogram meters squared. So this is the rotational inertia of this combination object. Now you might be saying, wait a minute, that's a huge number compared to the ones we got in the lab. But look at the numbers. Right? We're using 2 kilogram masses. We didn't use anything even close to a kilogram in the lab. Right? And this rod is 4 meters long. 4 meter sticks. Right? So these things are hugely far apart. Okay, so much, much different object. You think of this as like a barbell that's 4 meters from end to end. All right, it's going to be very hard to twist, right, to turn and everything. So that's why this rotational inertia is much bigger. In the lab, we were using fractions of a kilogram, right, and we were fractions of a meter apart, at most 18 centimeters, right? So that's why this number ended up so big. Well, let's do a variation. What if the rod is now twice as long, 8 meters long? How much rotational inertia? Well, some of you might see this answer already, but just to work through it, right? Again, the rotational inertia would be through the center of mass here, as it says here, which would be in the center of the rod, symmetry. We already did the math, right? We don't have to do it over again. It'll be 1/2 ml squared in this case, except now L is 8, right, instead of 4. 1/2 times 2 is 1. 8 squared is 64 kilogram meters squared. Now note, the rod is twice as long, but the rotational inertia is not twice as big. Remember, it was 16 in part A. It's 4 times as big because it's L squared. Could you have figured this out without writing this out? Yes, if you're thinking proportionally. And they love to do those little kinds of things on, you know, AP kind of work. Good proportional thinking. Unfortunately, there's no concept builders for rotation. If he ever does, I'm sure it would be some proportional thinking ones on this kind of situation for point masses. Right, so again, it's 2 times 2 squared away, or 4 times as big of a rotational inertia. Well, if we go back to just a 4-meter rod, okay, what if instead of rotating about the center of mass, what if we were rotating it about one end, like here? See how it would rotate that way instead? What's the rotational inertia going to be? It's going to be the same. It's going to be bigger. It's going to be smaller. What do you think? Well, let's see what the physics tells us. Again, there's two objects, so the rotational inertia of 2 point masses is the sum from I equals 1 to 2 of all of the mi ri squareds. If we expand that, again, I'm going to drop the subscript on the m just to be fancy. Do you see it? Do you see it? Isn't that one 0? Because how far away is this from the axis of rotation? Right? 0. It's not. It isn't a distance away. And how far away is this one? Well, it's the entire L. Right? So it's ml squared. You remember before, what was it? Let's go back. It was 1/2 ml squared before, about the center of mass. Now it's ml squared, right, away. It's actually twice as much rotational inertia here. Right? So if we plug the numbers in, we of course get twice as big of a number. It's 32 kilogram meters squared. So that's kind of interesting. Even though we've eliminated one of the masses, right, because we're rotating or putting our axis of rotation right there, the other one is twice as far away now. Instead of being L over 2 away, it's L away. And as we talked about earlier, changing R has a bigger effect than changing M because R is squared. So we might have cut the effective mass in half, but we doubled R. 1/2 times 2 squared is 1/2 times 4 is 2, and so we get 2 times as big of a rotational inertia. Now, I mean, this gets a little tougher to think through if the masses aren't the same, right, and all of that, but I just wanted to show you some of these, A, just to how to calculate it all and write it out, but B, to kind of look at some of these things proportionally, right, and realize what it means that I is mr squared.